install it using sudo apt install?
I believe that you can. It's best to pick the latest version from GitHub. I think the link that I have shared on the course website points you to the latest installation from the GitHub, right? So it's best to go there and
Yeah.
install it. Okay,
Okay.
so if you so the typically this is the issue with um, apt installing. I mean any software from just using apt install, right? So you'll always get outdated versions because the distributions themselves will refer to certain versions of the package that they know works on the distribution, and this might not be the latest version. So it's best to install directly from the GitHub, where they release installers for OS X and Windows, and for Linux, I believe that you just install. I don't know what. I have no idea, but things work well on Linux, right? And then it's a challenge to get it working on other environments. Anyway, good. So let me start sharing. Okay. So we are. I'm hoping that we can finish the logic parts today. Okay. Apt install provides an older version. The latest one is 8.13. So yeah. So I should say that it doesn't matter that whether you install 8.10 or 8.13. The minor versions really shouldn't matter because um, because there is only improvements. So whatever works, right? I recommend installing 8.13 because I use 8.13. But if you cannot install 8.13 and you can only install 8.10, uh, I mean, it's a small class. I can help out, right? Just DM me on Slack, and then we can sort it out. Okay, good. So let's continue. Okay, so we are looking at conjunction, disjunctions, and other things in the last class. Um, the general theme is that these operators, right, which we think of as primitives in a propositional logic language, are all encoded as basic inductive data types, right? So far, and what you will see is that the rest of the operators, right? So they are also built as what you would consider as primitives in a propositional logic or a first order logic, are all simply encoded using inductive type definitions and functions. And it's surprising, right? Because it is sort of we always learn logic as okay, these are the primitive operations and here is how you reason about it using syntactic rules. But given that there is a smaller core, right, it makes everything become much more nicer to deal with, in the sense that uh, there are only fewer primitives, right? So you can actually reason about more complicated things using the basic primitives. And eventually, at the end of this lecture, you'll see that everything in Cox's logic, right, is encoded just with inductive types and functions, right? And it's a really nice application of Curry-Hewitt correspondence, and very nice practical application of what Curry-Hewitt correspondence means. Um, so yeah. So anyway, let's continue. You will see more of it. And the first one is we have these primitive truth values in logic, right? False and true. So let's look at how false is represented in Coq. So as I mentioned, there is capital false with the capital F and true with the capital T, and also false with the small f and true with the small t. When you look at false here, that's a Boolean value, right? And when I write false with the capital F, that's a proposition. We won't use these Boolean values that much. I mean, maybe never in this course. But remember that these two are two different things, right? One is a Boolean value, another is a proposition. Again, Boolean value is just a program term, and a proposition is what you can prove, right? And and false is something that you should never be able to prove, right? Because it's false. If you can produce evidence for false, then your whole system breaks down. We will see some of that now. But how is false actually defined? If you look at the definition of false, it is quite surprising, right? It just says inductive false. Inductive is a type definition. It says it's a proposition, but it doesn't have any constructors at all, right? This is not a typo. This is actually how false is defined. So if you sort of recall your understanding of how we defined uninhabited types in 3100, basically what this means is false is a type for which you cannot have any value at all, right? And that precisely captures what false should mean. So you can have something that is false, but you never will be able to produce evidence because there is no way to construct evidence. It's just not defined. This is valid syntax, and this is precisely how false is defined, right? And what that means is that if you can produce evidence for false, then the whole system breaks down, right? False implies anything, right? Um, yeah, so we can try to show that false implies any proposition. So we call this explosion, right? A principle of explosion, which just says that for any proposition at all, if you can provide evidence for false, which you cannot, which you should not, right? Then you can prove P. So the other way to read this is false implies anything. So how does the proof actually go through? So again, we have two introductions here, right? And one for this P and one for the antecedent of the implication. Let's introduce both of them. And we have this new tactic, which is called contradiction, which basically searches for contradiction in the assumptions. So contradiction is anything that can derive false by function application or just the constant false, right? I'm saying I hold the evidence for false, which is not possible at all. So Coq just says, okay, if you have evidence for false, which you should not hold, then anything else holds. And contradiction is that way of reasoning. And when you do contradiction, you can prove anything at all, right? I want to prove P. I somehow have gotten the evidence for false, which is false holds. And contradiction says, okay, if you have evidence for false, then everything else breaks down. So you can prove P, right? And contradiction is just a tactic that searches for contradictions in the assumptions, right? If you look at how the proof is constructed, it will sort of mirror what we've seen earlier, but it also has a new thing. So we have a for all P and a false, right? Uh, for that, we have a P proposition. So assume that there is a P proposition and you are provided an evidence for false, right? This function can never be applied, right? And it is assuming that you have this evidence for false. We are using this thing called false induction. This ties to induction, but the way you should think about it now is false induction is this magic function, right? Which given the evidence for false, it can prove any proposition. So that is some primitive. Assume that it is primitive. It is not, but it is just a function that given the evidence for false holds, it can prove any proposition at all, right? We are using false induction here. Let's actually look at what false induction is. So false induction takes some proposition that you want to show, some evidence for false, right? It does a pattern match on F, right? F is this evidence for false. Recall that we saw that there were no constructors for false, right? And essentially what this says is, I have some evidence for false. That is not possible. So because there are no constructors, so I'm just having an empty pattern match here. And this return P, this is the last time you'll see it. We won't look at it later. It just says that I'm going to produce a value of type P. This is just magic, right? You're just bringing it out of nowhere. You're just saying that if you happen to have evidence for false, I'm just going to make up a P and return it. And this P could be anything at all, any proposition. Right? We'll come back to false induction when we look at induction in a little bit more detail. But these false induction is a thing that is constructed from looking at algebraic data types. So when you declare an inductive type, Coq automatically has some rules in order to create these induction rules. And we are just using that here, right? So some digging in, but details are not important here. But the takeaway is this, right? So if you want to prove explosion, right, this is the same theorem as previously written down. For all proposition, if false holds, then P, you can just write a function directly, right? Fun, which is prop P matches this P here, this argument. And the second one is evidence for false. There are no values for false. You just pattern match it with an empty pattern. You can just say, oh, I'm just going to return P, right? So this is this is needed, right? We want to prove by contradiction. So we want to have proofs, um, being able to express proofs that involves false, but you wouldn't be able to apply this function at all, right? This particular function, because you cannot have a value that has this type. Keep that in the back of the mind. I think the takeaway is that that's the only thing, right? And if you sort of take this idea that for false you cannot provide any proof, then this particular theorem, right, it says that for all P implies P and false, you cannot prove this theorem, right? Why can't you prove this theorem? If you sort of go back to your way of thinking about it functionally, so this is just a function argument, right? So you're given some proof of P. Oh, I have this P in hand. I have to create a conjunction. The way you create a conjunction, proof for a conjunction is you have both the left-hand side, proof for left-hand side and proof for right-hand side. I have the proof for left-hand side, which is P, but I cannot create the proof for right-hand side because it's false, right? It doesn't have any inhabitant. So if you try to prove it, what you will end up is you will get stuck, right? You can just use tactics. So we introduce two introductions, one for P here, and one for this P, which is the proof of P. So we call it P holes. So how do you deal with conjunction in the goal? You split it, right? You have to show both the cases hold. We split it. Our first sub goal says, "Oh, show me the P holes." We have that proof in the assumption, so assumption makes it go through. And the next sub goal asks us to provide evidence or false, and we cannot, right? We have what do we have in the assumption? We have P holes, but nothing. We are just stuck here, as we should be, right? This is what we expect. So you cannot show that P implies P and false holds in holds, because that doesn't hold in propositional logic as well. But we can show that P implies P or false. Right? Why is this case? If you have evidence for P, then for conjunction, I only need one of the components, right? I can always choose the left component and then give P as the evidence, which is what we do here, right? We do the introductions, and then I need to show P disjunction false holds. I'll just choose to show that I can show P, right? So I apply the left tactic to choose the left one, and assumption makes it go through, right? So this is simple proofs of dealing with false. So we've seen false, right? False is something that never holds. But what is true? True is something that always holds, right? Whenever I want to show true, it just holds by fiat. So how is that represented? True is represented as an inductive type, right? Which has exactly one constructor. It's called I. You can think of that as some value, right? Which has the type true. Whenever you want to show true, you can just produce this I as the evidence. This is the value, right? Um, so here is some simple proof about P implies P and true, right? Recall what you have to show. For conjunction, you have to show both of the components. For P is given as the argument to this function. So you can just return that P. For the right hand side, we know exactly what the evidence for true is. That's just the constructor, right? If you produce I, then you have true. And this is precisely what we are going to do. So you do the introductions here, right? You do the introductions. We have this conjunction, you split it. You have two sub goals. As earlier, you can make this proof go through by assumption tactic, right? And for true, how do I show true? I know exactly what the constructor is, right? So there is this new tactic called exact, which just says that the proof of the goal, right, is this exact term. You construct a term and then say this is the exact term whose type is the goal that you want to prove. And here it is very simple because we know that I constructor is the only constructor for true. Exactly I makes the proof for true both. So that's basically that. And yeah, so any questions on true and false so far?
Casey, you mentioned the constructor I, right? I want to know what the
Yeah,
significance of that is. Is it called I in the library itself, or is there something more to
it's
it?
part of the. It's just called I in the library. I don't know why it's called I. Yeah, but it could be any name at all, right? And it's just I.
I see. Thank you.
You could have named it. Excuse me. You could have named it other things as well, and you can build your own true, right? And you just produce this I as the evidence. We will see this exact tactic later. I mean, basically the idea of introducing true and false is basically to introduce the other tactics that we use to operate with true and false.
Yeah, so I was
Okay.
actually going to ask that next. The exact tactic, can it be used even on types that we have defined, wherein the
Yeah,
proof
you
might follow?
can. Yeah, you can. So if you want to show something of type whose which is the goal that you want to prove, you can just exactly write the term, right, and that one goes through.
Mhm.
So yeah, so these are like functions, right? Essentially, exact is a function that takes some term, and what it does is it looks at the goal and it looks at the term that you're providing, and what it expects is that the type of this term matches the goal that you're trying to show, and if it is, then it goes through. Yeah, if you use, you can use other things, right? But oh, nil is not there. Maybe I'll do. Okay, this is not there. Yeah, you can apply other things, but essentially it won't go through because that's not the proof. Okay, so that is true and false. Let's the other thing that we have not seen so far is negation, right? In Coq, the way we write negation is this tilde, right? So tilde means negation. So let's and that is just a syntactic sugar. So let's locate where tilde is. Whenever you read tilde x, you read it as the type not x. And what is not? So not is special, right? So not is um, a function actually. So everything else that we've seen, conjunction, disjunction, false, true, and everything were inductive types, right? Not is the first one that happens to be a function representation, right? And not takes a proposition and returns a proposition, right? That is fine. And the way not is actually represented is that give me a proof for some a proposition, right? And what I give you back is this way to construct a to false. Essentially, not is just a to false, right? If you have a proof for something, and if you can derive false from it, then you have a proof for the negation of it, right? If I have proof for true, and if I can derive false from it, then essentially I have a function, right, which given true gives me false, and that is precisely what the definition of not is. The way to think about it is not is just a function which is right. So and and it has some interesting implications. So again, we are going to see a new tactic, and that is why we are introducing not here. So here is some theorem, right? So if I mean, I'm sort of writing not false here, but essentially anything implies true, right? So because you can always show true by exact I, anything at all implies true. But here I'm saying not false implies true. This is just to show how to deal with negation in tactics. So I'm going to show not false implies true. So we are going to see a new tactic called unfold. This unfold tactic is the way you should think about it is it is doing substitution of the function definition in the body of the goal, right? So this negation, right, is a function as we've seen just now. So all we are going to do here is to unfold not so that it becomes obvious what the construction is. You're just expanding it in place. So when you unfold not, this is false, right? And negation is always defined as whatever you have here implies false. So when I unfold not, I get false implies false, because that is how it is defined here, right? It is some not is defined on some A, and all you have defined is A to false. And we have not false here. So when you unfold it, because that's a function, you're just going to have false implies false. Okay, I have false implies false. What do I do with it? I do the introductions, but I'm actually not going to use this hypothesis at all, because anything implies true. And the way anything implies true is I know exactly how to prove true, which is using this I constructor, right? I have exact I, so I just give that proof, and the proof, the whole proof goes through. If you look at, I mean, the thing to observe here is at this point, right? I introduced a hypothesis, but I'm not using the hypothesis at all. And you can see that in the construction of the proof. So I'm just printing the proof for not false. And the way you observe that is it takes evidence for false implies false, right? So it's a function that takes evidence for false implies false, but actually ignores it, right? This underscore symbol here is just ignore the argument. I'm not even naming it. And all I'm doing is I'm just returning this I, which is the proof for true. And hence you have the proof for not false implies true. Okay. So yeah, so the fact that you are not using a hypothesis here is reflected in the fact that you are not using a function argument here. That's sort of the analogy that you should pick up. Let's prove something more interesting, right? So if I have evidence for not true, then it implies false, right? So just thinking about proposition logic, this should be obviously true, but there is no obvious here, right? We have to construct it from the basic knowledge that we have in Cog. So let's look at this proof. It's actually an interesting one. So we have a negation here. We know negation is a function. So we first unfold negation. So we get true implies false. Let's introduce true implies false, right? I have something which, when given true, returns me evidence for false, right? And I'm going to, so I need to show false, right? I'm going to apply backwards reasoning here. So I'm going to use the apply tactic. In order to show false, I have something that is true to false. So I'm going to show true. And I'm going to do that using the apply tactic, right? When you apply, your goal actually changes to true because you applied this thing backwards. And true, we know how to show, right? You just show true by exact type. And your proof goes through. The proof that it produces is the interesting one. The tactics that you use to get to the proof is okay, sort of interesting, but the proof is actually very interesting, right? So how does the proof actually go through? We said we have evidence for some function that goes from true to false, right? Which, when given true, returns you a false. And what we have to return here is false, right? And the proof itself is quite interesting. So it takes some higher order function, right? True implies false, right? That is exactly not true. And I need to produce false as a result. And the way I produce false as a result is I just apply it to whatever whatever is the proof for true. I is the proof for true. So if you apply that to the function true implies false, you get a false as a result, right? So this is quite interesting because you cannot construct this function, right? And the way to read this is, if you had a function like that, then we can derive false, right? And you cannot create this function because you essentially, it just takes a true. You have to produce false. I mean, that function does not exist. But if you had such a function, then I can just apply I to that function to get a proof for false. And that's the proof for not true implies false. Right? The thing to take away here is that things that we think are so fundamental in propositional logic are actually constructed from basic primitives, right? Where we actually do everything in this constructive way. So that is the thing that you want to take away in this particular example, right? Okay, so and let's prove one more theorem. So this says contradiction implies anything, right? So if I have the proof for both the P and not P, right, I can prove anything at all. If you have P and not P, then it means false, right? Some proposition cannot be true and false at the same time. But if you had such a proof, then you can prove anything at all. So we just pick Q as the argument. This is again explosion, right? If you had this, you have false, and then you are producing proof for something, anything at all. So false implies anything. That is why this proof holds. Let's look at how we prove this, right? So do the unfolding of negation here first. So unfold not. Do all the introductions. I'm not naming anything here. So you have 1, 2, 3 introductions. The third one is this entire thing, right? And now we have a conjunction in the hypothesis, right? So we destruct this hypothesis. If you destruct it, you will see that you have evidence for P and you have evidence for P implies false. This you can derive contradiction from, right? So contradiction. Essentially, I have a value whose type is P. I have a hypothesis, which is if you have P, then you can derive false, which means that you can apply H0 on H and derive a contradiction, right? So, and that is what we are going to use here. But contradiction tactic also does these applications. So it searches for suitable applications to derive false. And if it detects such a contradiction, then it makes the proof go through, right? So that is why this proof goes through, right? So, but you can be very explicit as well. I think we can do apply H0 in H, right? You get a false. And now contradiction just searches for this false and then makes it go through. Right? So what we are actually using here is the fact that one is just a proof for P. Another is a function. Whenever you see a negation, it is a function that when given a proof for P, it gives you a false, right? And we are just taking this and applying it to this function and deriving false, and false implies anything. And that is why this proof goes through, right? So that's the idea there. Any questions on this one? This is sort of this is nicer because rather than just taking these assumptions by fiat, right? Oh, if you see P and not P, then it implies anything at all. We just say, oh, it implies false, and hence things hold. We actually have these things which are programs, so we manipulate these things in practice, right? So which is quite nice to do. Any questions?
Casey, I had a couple of observations.
Yeah.
In the theorem for not true, right? If you can go back to.
Yeah.
So here you don't. There's not a mandate that you need to use apply here, right? Even here you could have used contradict directly, because you have to false there.
Yeah. Let's see.
Once you intros T implies false, right? You can just
contradiction. Yeah. So that goes through as well. Yeah, I think contradiction is also. Contradiction knows that when you have true implies false, it knows that it can apply the evidence for true, which is I, right, to this function. So that is what it knows internally, and that is the reason why this proof goes through with contradiction.
Okay, and the other thing is in the original form of the code, it's whatever you have here on the screen.
Yeah.
So the thing that's kind of tripping me up here is when you did the apply of T implies right. So here we essentially applied an assumption that we know is false, or rather that we know is invalid, right? Because true implies false is the assumption there that we
I
introduced.
think that is what we have in the assumption, right? That is why this proof actually, this theorem is actually provable.
Right. So what I'm going to ask next is, doesn't that kind of open up a can of worms where when you're trying to prove a theorem and you can assume something that's obviously false if it satisfies you?
So that is part of the assumption, right? So this is basic logic. So if you have something in your part of set of assumptions which lead to contradiction, then you can prove anything at all. I mean, this is just a fact of just logic, right? So I want to express a logical statement, and I have something which is it says Schrodinger's cat is dead, Schrodinger's cat is alive, right? And that implies that universe is finite or something. This might be true in quantum world, right? But in our world, this cannot be the case, right? So you get a false out. But this assumption is part of the theorem that we are proving. Assuming that this holds, then universe is finite, right? And the assumptions could be invalid. They can derive contradiction. That is fine. They are not opening a can of worms. You just have to be careful in when you write larger proofs. You have to be careful that your assumptions are internally consistent, right? So you build something that is that makes sense, and if they are not internally consistent and you can derive false from it, you can prove anything at all. That's just a fact of life, right? So it's not something specific to COP.
So it's just that we need to ensure that our body of assumptions is consistent within itself, even if every single thing might be invalid. We just have to agree with this.
Yeah.
Okay.
And I don't think this would be a problem in practice. It's hard to, if you set up your, I mean, we'll see more examples as we see larger programs and proving interesting properties. If you set up your system in such a way that you won't end up making these internally inconsistent issues and so on. So I think we will make sure that that doesn't happen. It's hard to do that, right? It is actually really hard to set up inconsistent systems and then make the proof go through. We'll see some of that. I think it will become more obvious as we look at larger, more interesting properties. Good question. Okay, so I'm going to have a sort of a digression, but this is an important digression. So we know De Morgan's laws, right? So this says negation distributes over disjunction. Negation of P and P or Q implies that negation of P and negation of Q. The way to read this is if P or Q leads to an explosion, then P leads to an explosion and Q leads to an explosion. Right, so let's prove this. I mean, this fact itself should be fairly obvious. We know that this holds from logic 101, right? So you unfold not first. All of these things get unfolded. Then we introduce PQ, and then P or Q implies false, right? P or Q implies false. So I have a conjunction here. So I split it so that I have two subgoals. And then I do the introductions, right? So I split it. I have two subgoals, and then I'm using this bulleted thing to focus on one subgoal at a time, right? Focusing on the first subgoal, I have one more introduction, so let me introduce it. I need to prove false. I have P or Q implies false, so let me apply it to do backwards reasoning, right? I need to show P or Q now. I have P, so let me choose the left one. And then by assumption, things go through. Okay, so that's the first one. Second one also goes through in a similar fashion. So do the introductions, do the backwards reasoning. Here I need to show P or Q. I have proof for Q, right? So I choose the right one to prove. And then the proof goes through. Right? So this is fine. This is simple. I think nothing surprising here. So let's also prove the other De Morgan's law. Something interesting happens here. So we have, so all it is saying is negation distributes over conjunction as well. And what you get is negation of P or negation of Q, right? So let's see whether the proof goes through. So we're going to do the same thing, right? So we're going to unfold not. We are going to introduce our assumptions and these for all variables. So I have a disjunction here. I can choose to prove either one, right? I'm going down the left route. So I'm going to choose the left one. And then I have P implies false. So let me introduce P. And then I need to show false, right? So let me do backwards reasoning. Okay, that's fine. And then I need to show P and Q holes. I can split it. I have two subgoals, one of which is P holes. I have the proof here, right? So I can just use that here directly. So assumption makes it go through. But for Q, right, we don't have any proof for Q. We only have proof for P. And I have no way to proceed. Right? So this is surprising because we were able to prove the one of the law, but not the other one. Actually, here I chose left. Right? At that point, I'm choosing left here. If you choose the right one, you would end up with the same situation. You can try that on your own. Essentially, there is no way to make this proof go through in COP. Right? And you can ask why. Why is this a problem? Because if you intuitively think about it, in Cox's constructive logic, the way to read this is if the evidence of P and Q, the combined evidence of P and Q would lead to an explosion, then either P leads to an explosion or Q leads to an explosion is not valid because we start with the assumption that we have to have the thing that we have in the assumption is that once we have the evidence of both P and Q leading to an explosion, right? That is what we have in the assumption. Then we cannot claim that P independently leads to an explosion or Q independently leads to an explosion, right? That's just not a valid one. It is the combined evidence of P and Q that produces the explosion, and nothing is said about them individually, right? And the fundamental reason why we are able to prove one of the laws but not the other one is that Koch uses what is known as constructive logic. This is different from classical logic, right? Constructive logic is what we've been seeing all along. So whenever we want to prove something, right, we actually produce evidence as a term. We use Curry-Howard correspondence, right? Whenever we want to prove a proposition, which is just a type, we actually say, okay, here is a term which has the type, and that is the proof, right? Whenever we say we have a proof, we actually have a proof term in our hand. And that is not true with classical logic, right? So here is theorem of excluded middle, right? This is property of excluded middle. In classical logic, given a proposition, right, it is either true or false. It is you have a proposition, you can either prove it true or prove it false. Hence, the proposition that for all P or not P is true, right? Because every proposition that you can produce in this classical logic is either true or false. But this is not true in constructive logic. In constructive logic, you actually have to provide the construction, right, an evidence for P in order to show P, right? This is the fundamental difference between constructive logic and classical logic. Koch uses constructive logic. So this particular theorem does not hold. You can try to prove it, but you will get stuck. So we want to show P or not P holes. So you can introduce P. You can choose either one, right? If you choose left, you have to prove P. And the only way to prove P is by producing evidence for P. And we have no way of producing evidence for P. And similarly, the right also, you will get stuck. You can choose negation. You can unfold not, right? P implies false. And then you can do intros, right? I need to show false, but I have no contradiction in my assumptions in order to derive false. So I'm just stuck, right? So this is the fundamental difference, right? This law of excluded middle is not a thing in constructive logic, and the reason why Hawk uses logic is because we want to. Sorry, you might have lost me there for a second. So the reason why Coq uses constructive logic rather than classical logic is that we are going to use proofs of programs, right? We are always going to um, verify programs, and there being able to construct proofs is very important, right? So we will come back to this later. Why it is important? Because we actually manipulate the proof terms. That is how we build the proofs, right? So we cannot prove things like P or not P is always true. But Coq has, if you all you wanted to do was classical reasoning, right? I just want to use Coq as a thing for classical reasoning. You can open this module up, which is called Coq.logic.classical, right? And I'm opening this module so that I don't pollute the rest of the file. So a new module, which we just name it as Let's Do Classical Reasoning. And I import Coq.logic.classical. And if you look at what it brings in, it actually brings in just one axiom. Whenever you see star 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 in Coq, you read it as axioms, right? Those are taken as true by fiat. So in classical logic, the law of excluded middle is fiat, right? Once you have law of excluded middle, everything else is provable, including De Morgan's two law which we weren't able to prove. You can try that, right? I'm not going to spend time on that. Coq does allow you to do classical reasoning, but everything in Coq is basically constructive logic, right? So that's the thing to take away from here. So I mean, it's sort of it's a beautiful thing that we have with constructive logic, in the sense that whenever you have proof of something, you actually have a term that you can manipulate, right? So that's a nice property to have. This axiom has no proof term, right? We just take it as granted that this holds. We don't have a proof term that we can manipulate. We cannot print the proof of this because it's an axiom, right? So that's the digression to why I introduced De Morgan's laws. Yeah. Any questions on that? Okay, the main takeaway there is Coq uses constructive logic. Keep that in the back of the mind, right? We won't appeal explicitly to that, but we will come back to it often in the sense that anything that we do, we implicitly are working with constructive logic, right? So this thing is not proven. Okay, so the last thing I think we want to do is to circle back to equality and implication. We had seen equality earlier, right? I'm going to come back to that just to show you how equality is constructed. So we construct equality by using equals, right? So if you look at equals, the thing that we want is the second one. Whenever you see x equals y, you read it as the type EQXY, right? It has an implicit argument, so I'm going to use add to print the thing that we want to see. If you check at equality, it's basically constructor, a type constructor, right? That takes two values of type A, right? That can be anything at all, and it returns your proposition. A proposition is something you can prove, right? So I'm defining EQ42, right? So EQ42 takes a type, right? The type is going to be natural number, so that's the natural number argument here. And then I'm going to provide partially apply this function. Essentially, I'm just going to apply the first argument. I'm not going to apply the second argument. So I'm constructing EQ42, right, which is takes in a natural number, right, and builds a proposition, which basically you can prove or disprove, and internally it has 42 in it, right? So, for example, you can apply this function EQ42 to 42, and what you have as a proposition here is 42 equals 42. I should be able to prove this, right? 42 equals 42 is true. You can also construct propositions which are 42 equals 43. The way you do that is apply this function to 43, right? And you get a proposition, but internally this proposition represents 42 equals 43. This is the same as what you would have, the term that you have here is what you would have gotten if you have 42 equals 43, right? So we are just constructing propositions here. So how do you actually go ahead and prove this? If you print the term EQ, right? Equality is actually defined as an inductive type, right? Equality is defined as an inductive type that for any type takes a single argument x, right? And the only way to construct proof of equality is using this EQ-REFL constructor. And the EQ-REFL constructor just says x equals x. So observe that it only takes a single argument, right? So if you want to construct proofs for, say, 42 equals 42, you can use this EQ-REFL constructor this way. So if you look at EQ-REFL, it takes a type, it takes a single value, and then gives you that equality is reflexive. Essentially, you can apply it on any term at all, right? Here we apply it to 42. I apply EQ-REFL to type as a natural number that corresponds to this term. And then I apply 42. What I get back is a proof that 42 equals 42. The clever thing here is that this EQ-REFL constructor only takes one argument, right? You can only construct proofs for something equal to the same thing. You cannot ever construct a proof for 42 equals 43. That's just ruled out. So what does this all mean, right? So if you want to prove that 42 equals 42, right? I want to show that 42 equals 42. Trivially, this proof will go through, right? So if I just apply trivial, the proof will go through. But really what is happening is we are constructing a proof, right? That I'm building a EQ-REFL 42, which means it is internally building a term which is the evidence for 42 equals 42, right? And I use this exact term as a proof for 42 equals 42. So this is going to construct a term whose type is 42 equals 42, right? And Shashin, this is another example of how we are using exact, right? You don't need to use exact here. We can use simpler terms, but anyway. So we want to show something that has the type 42 equals 42. I'm just using EQ-REFL 42 here, and that makes the proof go through. And for this reason, we cannot prove 42 equals 43, right? Because we cannot construct the term. The only way to construct terms which have the EQ type is using the EQ-REFL constructor that takes exactly one argument, right? So we cannot ever construct 42 equals 43, proof for that. And hence 42 equals 43 is not true, right? So that's sort of the reasoning we use for equality. And the main takeaway is this, right? Equality is also just an inductive type. It's not baked in. Whenever we say P equals Q, all we are saying is give me an evidence by which I can construct this EQ-REFL value at the end of the day, right? So that is equality. And the last one that I want to cover is this implication, right? So it turns out implication is also defined, right? So implication is not fundamental. If you look at implication, implication is just defined as a function, right? This for all is also just a function. So the way to read this implication is that if you give me a proof for A, I will transform it into a proof for B, right? I won't tell you how, but I will just transform it into a proof for B. And the way you represent that is just this function type, which is for all A, give me an A, I will just give you a B. There might be a lot of terms that have this type. I mean, not this arbitrary A and B type, but there may be a lot of terms that have evidence for these sort of types. And essentially, when you look at implication, all it is saying is just a function definition, right? So just to drive this point home, here is P and Q implies Q, theorem, right? For all P and Q implies Q, right? The proof for that is very simple, right? So you have PQ that correspond to this for all, and the evidence for P and Q, and we know that this conjunction is built with the single constructor, right? Conj, which is evidence for P and evidence for Q, and you return the evidence for Q, which is what is expected on the right hand side, right? This is equivalent to this implication. You can just rewrite it as for all here, right? So for all underscore P and Q, I don't care what the argument is. I'm just going to name it, leave it as unnamed. But this term is the same as this term is what I want you to take away. And how do I show that it is the same term? The same proof will make this definition type check, right? So I'm taking the definition of P and Q implies Q, and I'm just giving the same term here that has the same type. So the takeaway is that implication, whenever you see P implies Q, that is also just a function definition. That is just a for all something Q, right? So what is the high level takeaway from this lecture? We saw a lot of tactics, right? How to manipulate these terms, which will all come in handy. But the key takeaway is that in Cox logic, equality, implication, conjunction, disjunction, true, false, negation, right, are all just implemented on top of inductive definitions, right? These algebraic types that we sort of define. And for all, there is a universal quantifier which we use here, right? Just with the universal quantifier and inductive definitions, everything else is defined. And that's the key takeaway from this lecture, right? So the language is like very, very small underneath. And lot of the things that you see on top are all just syntactic sugar, right? To make our life simpler. But the logic is like very tiny underneath. Actually, inductive types can also be encoded, right? So there is a nice encoding in an extension of simply typed lambda calculus called f omega, where you can also encode inductive types. But Coq doesn't do that because for performance reasons. But basically, when you have universal quantification and lambdas, right, you can encode anything else, everything else that you want in the first order logic. And that's a really nice idea. I think we won't discuss too deeply about that. But as we've seen, the key takeaway is this, right? All of these are just encodings. Nothing is primitive. Okay, so that concludes this logic lecture. There is a lot more in the actual file. So I'm editing this file called logic_lecture.v. In the same directory, there is a file called logic.v. There are more stuff there which you might play around with. Okay, so I think give that a try. See whether there is more to learn, right? But I'm not that. It is all sort of. I've covered everything that is important, right? So I think if you just go through this file, you should be fine. So in the next class, what we'll do is we'll look at induction, right? So induction is when things get pretty interesting, and induction is when writing proofs on paper breaks down. So once we start looking at induction, you will see the real use of using a proof assistant for doing proofs. We'll cover that tomorrow. Okay, I'll stop here. Any questions? Okay, if there are no questions, there is going to be one assignment on logic and one on induction. So I'm going to combine that and release that on Thursday. So you'll have an assignment every week. They won't take you a long time. It's just to make sure that you have this practice of doing proofs, right? And we'll see more stuff, more interesting stuff once we finish induction. We'll actually go to proving stuff about programs. Okay, so thank you very much. Let's stop here. Bye-bye.